In 1560, a Ukrainian peasant family began digging into the side of a hill. Monastery records document what happened next in precise detail. The pit measured 1.5 metres deep. Floor area 4 metres by 6 metres. Construction time 860 hours over 3 weeks. Materials required 3 to 4 cubic metres of clay, 2 cubic metres of wood, reeds harvested from 1,000 square metres of marshland. When they finished, this family had created a shelter that would house them through 21 winters. Through the Little Ice Age, through Tatar raids that destroyed their neighbours, through famines that killed half the village, that structure still exists today. 465 years later, in 2019, archaeologists measured the interior temperature, 8 degrees Celsius in winter, 12 degrees in summer. No heating system, no cooling, no electricity, just earth, wood and physics. This is engineering so sophisticated that when researchers at the Czech Republic's Archaeological Open-Air Museum reconstructed these structures using documented medieval methods, they discovered knowledge we had completely forgotten. Knowledge about thermal mass, about passive ventilation, about reading soil like a blacksmith reads metal. Today, we rebuild that knowledge, step by step. Section 1. Why dig down instead of build up? To understand 860 hours of digging, we must first understand why medieval people chose to go underground. The answer lies in 3 brutal realities. Problem 1. Thermal survival. Medieval Europe experienced the Little Ice Age from 1300 to 1850. Winter temperatures dropped 2 to 3 degrees below modern averages. In Eastern Europe, this meant -35 to -40 degrees Celsius for weeks at a time. A wooden house above ground loses heat through every surface: walls, roof, floor, wind, penetrates gaps between logs. Heating such a structure required burning 5 to 8 cords of wood per winter. For a peasant family, this was impossible. Most had access to perhaps 2 cords maximum. But the earth itself maintains constant temperature below 2 meters depth. This is geothermal reality. Soil temperature at 2 meters matches the annual average air temperature of that location. In Ukraine, that meant 8 to 10 degrees Celsius year-round. By digging down just 1.5 meters and covering the structure with earth, medieval builders eliminated 80% of heat loss. The structure no longer fought the winter. It used the earth as insulation. Problem 2. Material scarcity. Building a wooden house above ground required 15 to 20 cubic meters of quality timber. Straight logs, 6 to 8 meters long, debarked and seasoned. In the plains of Eastern Europe and the Romanian lowlands, such timber did not exist. The landscape was open steppe with scattered willows near rivers. But digging required only a shovel. The excavated earth became the walls. Local clay sealed the gaps. Marsh reeds provided roofing. Wood was needed only for support posts and the door frame. A 6-metre dwelling required just 2 cubic metres of timber instead of 20. The mathematics were brutal. No timber meant no surface house, but everyone had dirt. Problem 3. Survival during raids. The steppes saw constant raids from the 6th to the 16th century. Huns, Avars, Magyars, Mongols, Tatars, Cossacks. A wooden house above ground was visible for kilometres across flat terrain. It announced wealth. It invited attack. A dugout built into a hillside was invisible until you were standing directly above it. Smoke from the fire dispersed before rising above ground level. The entrance was narrow, easily defended. One man with a spear could hold the doorway indefinitely. Archaeological evidence shows this pattern repeatedly. Villages with surface houses were burned and abandoned. Villages with dugouts survived raid after raid. The invisible survived. The visible died. Section 2. The mathematics of 1.5 meters. The depth was not arbitrary. There is physics behind it. Excavations across Eastern Europe from the 6th to the 19th century show remarkable uniformity. Dugouts in Romania measure 1.4 to 1.6 meters deep. Ukraine, 1.3 to 1.7 meters. Southern Poland, 1.5 to 1.8 meters. Why? Why not dig 3 meters and gain more thermal stability? Why not dig only 1 meter and save labor? The answer lies in three physical constraints that medieval builders understood through centuries of trial and fatal error. Constraint 1. The water table. Dig too deep and you hit groundwater. In most lowland areas, the water table sits between 2 and 3 meters below surface. If your dugout floor reaches groundwater, the structure floods every spring. Families drown in their sleep during rapid snowmelt. This was documented in Ukrainian folk records as the spring death. Medieval builders had no instruments to measure water table depth, but they had observation. They watched where surface water pooled after rain. They noted where willows grew, indicating shallow groundwater. They dug test pits in late winter when the table was highest. Through this process, they learned that 1.5 meters was the safe maximum in most terrain, shallow enough to stay above the water table, deep enough to reach constant thermal mass. Constraint 2. Structural stability. Soil has a property called the angle of repose. This is the steepest angle at which soil remains stable without support. For most clay-rich soils in Eastern Europe, this angle is approximately 35 to 40 degrees. At 1 meter depth, you can dig nearly vertical walls. At 2 meters depth, the walls must slope significantly or be supported with timber. At 3 meters, collapse becomes almost inevitable without extensive reinforcement. Medieval builders had no knowledge of soil mechanics as a science, but they watched walls collapse. They saw families buried alive. They learned through death. The excavation pattern that evolved was this: dig to 1.5 meters depth. Slope the walls at 40 degrees. Reinforce only the corners with vertical posts. This created a stable structure with minimal timber use. Constraint 3. Air quality. At depths below 2 meters, carbon dioxide accumulates. It is heavier than air. It pools at ground level. A family sleeping in a 3-meter deep dugout could asphyxiate overnight as their own breath settled into a lethal layer. Medieval builders did not know chemistry. They did not understand CO2, but they knew the bad air sickness. They knew that very deep cellars made people drowsy, then unconscious, then dead. At 1.5 meters depth, natural convection still functioned. Warm air from the fire rose and escaped through the door opening. Cool, fresh air entered at floor level. The circulation was passive, but sufficient. This was the sweet spot. 1.5 meters, deep enough for thermal mass, shallow enough for water safety, stable enough for minimal support, ventilated enough for survival. The number was mathematical optimum discovered through centuries of building and burying the dead. If you're starting to see why medieval builders were smarter than we thought, a quick like helps this reach more people who need to know this. Takes 1 second. Section 3. The 860-hour construction sequence. Now we arrive at the actual work. The documented sequence that transformed bare earth into a dwelling. The process had 5 distinct phases. Each phase served a specific structural purpose. Each had its own failure modes that could kill you. Phase 1. Site selection. Hours 0 to 40. The builder searched for 3 specific features. First, a hillside with eastern or southern exposure. This orientation captured morning sun to warm the entrance. It positioned the dwelling away from prevailing north winds. Second, soil composition. The ideal soil was 60 to 70% clay. Pure clay was too hard to dig and cracked when dry. Pure sand collapsed when wet. Testing method. Dig a 30-centimeter hole. Fill it with water. If water drains in less than 1 hour, too much sand. If water remains after 4 hours, too much clay. If it drains between 1 and 3 hours, perfect. Third, drainage. The site had to be elevated relative to surrounding terrain. Even 50 centimeters of elevation prevented flooding during spring melt. Sites in depressions were death traps. Medieval builders spent days on this phase. Modern reconstruction attempts that skip site selection fail within the first year. Phase 2. Excavation. Hours, 41 to 380. The digging followed a specific pattern. Not random shoveling. A sequence. First, mark the perimeter. 4 meters by 6 meters was standard. This provided 24 square meters of floor space, sufficient for a family of 6 to 8 people plus stored food. Second, dig the entrance trench first. 1 meter wide, sloping downward from surface to the 1.5 meter depth over a 3 meter length. This provided access for removing excavated soil. It also allowed testing soil stability before committing to the main chamber. Third, excavate the main chamber in layers. Remove 30 centimetres of depth across the entire floor. Carry the soil out through the entrance. Repeat. This prevented workers from getting trapped in a hole with no exit route. The soil was not wasted. It was piled on the surface directly above where the roof would be. Later, this excavated earth would become the primary insulation layer. Excavation rate. 2 workers could remove approximately 0.5 cubic meters per hour in ideal soil conditions. The total volume was 36 cubic meters. This required 72 hours of pure digging time. But soil is never ideal. Rocks, roots, hard pan layers. The realistic time was 340 hours. Phase 3. Wall preparation. Hours 381 to 481 to 480 bited it. Now the walls existed, but they were raw earth, unstable. The medieval solution was wattle reinforcement. Drive vertical wooden stakes into the wall surface every 40 to 50 centimetres. The stakes penetrate 20 centimetres into the undisturbed earth behind the excavated wall. Between these vertical stakes weave horizontal willow branches in an over-under pattern, creating a basket-like structure against the wall. This wattle framework serves 2 purposes. It prevents loose soil from slumping, and it provides a key for the clay daub layer, applied next. Clay preparation. The clay was not used pure. It was mixed 50-50 with chopped straw. This created a composite material. The clay provided waterproofing. The organic fibre provided tensile strength and prevented cracking. Application. Press the clay straw mixture into the wattle framework by hand. Build up layers 2 to 3 centimetres thick. Allow each layer to dry for 1 day before applying the next. Total thickness 8 to 10 centimetres. This process consumed 3 to 4 cubic metres of clay and required 100 hours of labour. But when complete, the walls were sealed, waterproof, insulated, structurally stable. Phase 4. Roof construction. Hours 481 to 680. The roof had to support 50 to 100 centimetres of earth. It had to shed water. It had to allow smoke to escape, but keep rain out. The structure began with 4 corner posts. Each post was 15 to 20 centimetres in diameter, set 60 centimetres into the ground below the dugout floor. They extended 2 to 2.5 metres above floor level. Connecting these posts were ridge beams and rafters. The roof slope was typically 25 to 30 degrees, steeper than modern roofs to shed water and snow effectively. Over the rafters, builders laid a lattice of thinner branches spaced 10 to 15 centimetres apart. The waterproofing layer was birch bark, where available, or tightly woven reeds. Birch bark is naturally waterproof and resists rot for decades. In areas without birch, reeds were harvested from marshland, laid in overlapping layers 30 centimetres thick. This created a thatch roof, capable of shedding water for 15 to 20 years. Over the waterproof layer came the earth. This was the clay-rich soil excavated from the chamber itself. It was layered on gradually, 10 centimetres per week, to allow the roof structure to settle and adjust to the load. Final earth layer thickness, 50 to 80 centimetres. This provided insulation value equivalent to 2 metres of modern fiberglass. But it never compressed, never degraded, never needed replacement. Phase 5. Interior finishing. Hours 681 to 860. The fireplace was the heart of the structure. Location was critical, centred on the long wall opposite the entrance. This allowed smoke to rise toward a vent hole in the roof, while warm air circulated through the space. The fireplace itself was built from flat stones arranged in a circle 80 to 100 centimetres in diameter, no mortar, just carefully fitted stones. Smoke management was passive but effective. A small opening in the roof, directly above the fireplace, measured 20 to 30 centimetres square. This was covered with a wooden frame and removable stone slab, open during fire use, closed at night. Sleeping platforms were constructed along the walls, raised 40 to 50 centimetres above floor level. This elevation positioned sleepers in the warmest air layer, and it protected them from carbon dioxide accumulation at floor level. When finished, the interior measured approximately 2.1 to 2.3 metres from floor to roof peak, sufficient to stand upright in the centre. low enough to retain heat efficiently. Total labor, 860 hours. For 2 workers, this meant 430 hours each. At 10 hours per day, this was 43 working days. Exactly 6 weeks. The medieval record was not folklore. It was precise project management born from necessity. Section 4. The temperature knowledge in their hand. Medieval builders possessed thermal literacy, the ability to read temperature dynamics through observation. No instruments, just centuries of knowledge. Layer 1. Soil selection by season. The experienced builder dug in early spring, when the water table was highest and soil was saturated. If the excavated walls remained stable during the wettest conditions, they would remain stable year-round. If they slumped or wept during spring excavation, the site was abandoned. This required patience. It required delaying construction by an entire year to test during spring conditions. But it meant the difference between a structure that lasted 50 years and one that collapsed in 5. Layer 2. The clay cure process. The clay straw daub was not simply slapped on and left to dry. There was a curing sequence. During the first week after application, the entrance was kept partially covered. This slowed air movement. The clay lost approximately 5% of its water content. Slow, controlled shrinkage. No cracking. During the second week, the entrance covering was removed. Air circulation increased. The clay lost another 10% of water content. By the third week, the clay had reached equilibrium, moisture content of 8 to 12%. How did they know when curing was complete? The sound. Tap the wall with your knuckles. Fresh clay produces a dull thud. Properly cured clay produces a harder, higher-pitched sound. Listen to the material. It tells you its state. Layer 3. The thermal mass effect. Earth has high thermal mass. 1 cubic metre of soil weighs approximately 1,600 kilograms. Medieval builders did not know these numbers, but they knew the effect. The earth surrounding the dugout absorbed heat during the day and released it slowly at night. This moderated temperature extremes. In summer, when outside air reached 30 degrees, the earth remained 12 to 15 degrees. In winter, when outside air dropped to -30, the earth remained 5 to 8 degrees. The key was depth. At surface level, soil temperature fluctuates with air temperature. At 1.5 meters depth, virtually eliminated. Section 5. The ventilation secret. The knowledge of how air moves in underground spaces. How to prevent suffocation without creating unbearable drafts. This was passive ventilation. No fans, no pumps, just careful design working with natural convection. Component 1. The entrance geometry. The entrance sloped downward from surface to the dwelling floor over a distance of 2.5 to 3 meters. This created a horizontal to vertical ratio of approximately 2 to 1. Why does this ratio matter? A steep entrance creates high-velocity air movement. Cold winter air rushes directly to the floor, creating brutal drafts. A shallow entrance means smoke and carbon dioxide can accumulate. The 2 to 1 ratio balanced these factors. Air entered at moderate velocity, enough to drive circulation, not so much to create uncomfortable drafts. The sloped entrance created a cold air trap. Cold air is denser than warm air. When cold air enters, it sinks to the lowest point before entering the main chamber. This lowest point is the entrance floor, deliberately 20 to 30 centimeters below the main dwelling floor. The cold air pools in this entrance depression. It mixes slowly with the warmer air in the main chamber. Component 2. The smoke vent positioning. The vent was located directly above the fireplace, but offset by 30 to 40 centimeters toward the rear wall. Why the offset? When a fire burns, it creates a column of rising hot gas, approximately 40 to 50 centimeters in diameter. If the vent is positioned exactly above the fire, the rising smoke creates a vacuum. Air is pulled up too fast. The dwelling becomes drafty. The offset vent position forces the smoke column to deflect slightly before exiting. This creates back pressure. The smoke still exits efficiently, but the draw is moderated. The vent was covered with a wooden frame and a movable stone slab. This adjustability allowed the occupants to control ventilation rate. On extremely cold nights, the vent could be nearly closed, retaining maximum heat. On milder days, fully opened. Component 3. The stack effect. In winter, the interior temperature was maintained at 8 to 12 degrees, through minimal fire use and thermal mass. The exterior temperature was often -20 to -30 degrees. This created a temperature difference of 30 to 40 degrees across the roof structure. The warm air inside rose toward the roof peak. The smoke vent, positioned at the peak, became a natural chimney. The pressure difference between warm interior and cold exterior created a draft. The thicker the earth layer on the roof, the greater the thermal insulation and the larger the temperature difference. Larger temperature difference meant stronger draft. But if the earth layer exceeded 80 to 100 centimeters, the additional weight stressed the roof structure beyond safety margins. 50 to 80 centimeters of roof earth. Sufficient insulation to create strong thermal differential. Not so thick as to risk structural collapse. The result was a dwelling that breathed, air entered through the entrance, circulated through the main chamber, rose toward the smoke vent, exited to the atmosphere, all driven by temperature differences, all passive. Section 6. The proof. Archaeological sites proved the method worked. The Archaeological Open-Air Museum at Brezno, Czech Republic, reconstructed 2 medieval dugouts in the early 2000s using only techniques documented in historical records. No modern materials, no contemporary tools. Those reconstructions have now stood for over 20 years. Researchers have monitored interior temperature, humidity, and structural stability. The temperature data is remarkable. In summer, when outside air reached 32 degrees Celsius, the interior measured 14 degrees. In winter, when outside air dropped to -18 degrees, the interior measured 7 degrees. A temperature range of 7 degrees inside versus 50 degrees outside. The humidity data is equally striking. Exterior relative humidity fluctuated between 40 and 95% seasonally. Interior humidity remained stable at 55 to 65%. The earthen walls breathed, no condensation, no mold, no rot. The structural integrity has shown zero degradation. The wattle framework remains intact. The clay daub shows no cracking. After 20 years, the structure is as sound as the day it was completed. Compare this to archaeological evidence from actual medieval sites. Carlungi Earth House in Scotland was built approximately 2,000 years ago during the Iron Age. It is a stone-lined underground passage measuring 40 meters long. Today, it is open to the public. The structure remains completely intact after 2 millennia. If these numbers seem impossible, consider subscribing. Every video on this channel brings forgotten medieval knowledge back to life. The Vampire Dugout in Belgium was built in 1918 during World War I using medieval principles documented by German engineers. It was built 12 meters underground. After the war, it flooded completely and remained underwater for 90 years. In 2008, archaeologists pumped it out. The structure was perfectly preserved. The wooden supports had not rotted. It could have been reoccupied immediately. These are not isolated examples. These are the pattern. Structures built according to these principles survive. Structures built ignoring these principles fail. The knowledge was not mystical. It was applied physics discovered through observation and refined through centuries of iteration. The story of medieval dugouts is ultimately a story about knowledge that does not live in books. It lives in hands, in eyes, in the feel of soil and the sound of rain. When a medieval family spent 860 hours digging into a hillside, they were not just creating shelter. They were applying a sophisticated understanding of thermodynamics, soil mechanics, and passive environmental control. Understanding developed over 50 generations. Understanding tested by survival itself. We look at a hole in the ground covered with sticks and think, primitive. But there is nothing primitive about thermal mass calculations. Nothing primitive about understanding soil plasticity or optimizing ventilation geometry. The medieval builders did not have our tools. They did not have our materials. They did not have our theoretical knowledge. But they had something we have lost. They had intimate knowledge of natural materials. They had the patience to observe. They had the humility to listen to what the earth itself was telling them. Every time someone builds an underground structure, they are either working with these principles or fighting against them. The principles do not care about technology. They are physics. They are geology. They are thermodynamics. The dugouts survived because they obeyed these laws, not because of magic, because knowledge about how Earth behaves was encoded into every dimension, every material choice, every construction sequence. That knowledge still exists. It exists in the structures themselves. It exists in archaeological records. What does not exist anymore is the cultural transmission, the master teaching the apprentice. But perhaps, in understanding what has been preserved in dirt and stone, we can begin to ask what knowledge might be reclaimed. Not to live in holes, but to understand that knowledge about working with natural systems is knowledge worth preserving. 860 hours of labour, 43 working days, 6 weeks from bare ground to livable home, using only what the earth provided. That is not primitive. That is profound. Thank you for watching.